In this short video, we're going to review what I call the big three of evolution, and we're going to introduce and begin to talk about a online tool that you have available, and we'll be looking at it from time to time. I'm going to make this a little bigger. So you'll find a link for this evolution simulator under the additional resources folder. So if you look on the left-hand side here, additional resources, and in there you have the evolution simulator. So you can follow along or you can watch and then later on bring this up. You'll be using this at various times throughout the semester. So quick review, big three. The first one is mutation. Now we do have a simulation of mutation that is built into this tool here. You can use it. It's a little tricky to simulate evolution on this scale because evolution or mutations, I'm sorry, are random, and they can have any range of change from something really good to something really bad. So basically what we can do is we can simulate a brand new mutation at a small rate, and sometimes mutations happen. So this is a fairly large rate of mutation, 1 in 100. So basically this means that out of every 100 offspring that are born over the course of this simulation, one of them will have a mutation where if they have a little a, it will go to big A. And so if we run this simulation, we're going to start at 50-50. The default is 50% big A alleles, which of course means 50% little a alleles. We're just looking at a 2 allele system. All of the natural selection, which we have displayed here as fitness, will set equally. And then the default is 200 individuals in the population, a rather small population, and then 200 generations. Now, I'm going to change the default to a larger number, and the reason is if we don't, we'll have a large impact with genetic drift. We'll look at that in a little bit. But with mutation, notice that if we have a constant mutation rate, that we will just have fairly predictable. If we raise the amount here, if we change this to 0.2, we'll see the same effect, but at a higher rate. And eventually it slows down because we have fewer little a alleles. Now, a couple things I want to point out about this simulator. Number one, you can run multiple simulations and it will just continue to graph them so you can see whether you're getting the same thing over and over again or whether they're different. If you change the settings in between simulations though, so remember this green one was a mutation rate of 0.01, this is 0.02, a higher mutation rate. So if you change them, you just need to remember that because you're going to have different results. But you can clear it, and we can run the same thing over and over again. And you can see whether it's predictable, and if so, you'll get the same line. There's a purple one over the blue, and then green. You get the same thing over and over again. And so you can determine whether an evolutionary process is predictable or whether there's some unpredictability to it. Now, on the graph, we have a big allele frequency, so the big A, from 0 to 1. And then on the other side, we have the small one from 0 to 1 just reversed. And basically what this means is that we're going to start out at 50-50. If we move all the way so that the graph gets to the top of the chart here, that is what we call fixation or fixing the big A allele, which means we'd have it at 100%. And of course, at that time, you'd have 0% for the small a allele. So these are really just there for your reference. You could do the simple math. If you have 90% big a allele, you're going to have 10% little a allele. Okay. The other thing is over here, we have a Punnett square with a visual representation of a beetle, just to represent the trait here. And the trait in this case is the color of the elytra, or the hard covering of the beetle shell, where we have red elytra versus gray elytra. And this is a dominant recessive trait, so we've got big A, big A, big A, little a, big A, little a, right? Those are our heterozygotes, which because it's a dominant trait, they exhibit that dominant phenotype. And then over here we have a little a, which is a recessive phenotype. So hopefully you're somewhat familiar with that. If not, that's okay. We'll do a little bit more of it later. This is really just more of a visual one. Now you'll notice if we bring this way up, let's make this a 0.5, which is it's going to just shoot up dramatically. Once we get to fixation, which is hard because the allele is very rare, and so even though it's 50%, we only have a very, very tiny amount. But if we reach fixation, eventually we'd get this number all the way to 0. We only got it to 2 out of 1,000, right? 0.002. But eventually it was possible we could do it. Now, once that occurs, we've completely lost the big A allele unless there's a mutation that changes a big A back to a little a. We would then only have big A alleles in the population, right? So anyway, we can do some stuff with mutation, but it's fairly limited, so we won't do a whole lot more than that. So let's set this back to 0 so there's no mutation at all. And if we run a simple simulation like this, where we've eliminated genetic drift by making the population large, we have no natural selection because fitness levels are all the same. If we run this, we're going to get the same result time after time, right? It's going to basically be no evolution. We're going to stay exactly where we are. Now notice the population doesn't change. Generation after generation, we have the exact same thing. So now let's look at a very simple way of how we would implement the second of the big three, which is natural selection. If we change the fitness level, then we're going to have a change in the outcome. Now, a little quick word about fitness, and we'll come back to this later. By definition, a fitness level of 1 is the highest we can get. So mathematically, it's easiest if we represent these fitnesses as frequencies, with a 0 being 0 fitness at all, meaning you're dead or you're sterile. There's no way you can pass your genes on to the next generation. And 1 being the most possible, the 100% or the most fit phenotype. So when they're all at 1, it means everyone's equally fit, everyone does the same amount, nothing changes. But if we reduce the fitness of one of these, then we're going to see some different outcomes. We won't talk in a lot of detail about these patterns, but notice that we're going to lose one of the alleles if it's less fit. If we change it the other way, and we look at that, we're going to see the same pattern, but going in the opposite direction. Notice this is very predictable. If we change those, we're going to get a different curve, but then keeping them the same and running multiple simulations, we get the same thing generation after generation. Okay, so that's how you would do fitness, and you can play around with this if you want. You can say, well, what happens if my heterozygote fitness is less than 1, 0.95 is less than 1. Now, one of these by definition has to be 1, so if you try to change this to another one, it won't allow you to do it. It'll just switch back to 1, because by definition, whatever is the most fit phenotype is going to have a fitness level of 1, and then everything else will be scaled down based on that one. So you could look at this and see, oh, look, that changes it quite a bit. We have a little bit different curve than if we do something like this. So you guys can play around with this, but the point is that changes in fitness level will invoke natural selection, and that will cause a population to change over generations. Okay, so play around with that. We'll come back to it in later discussions and look at some very specific patterns. But for now, I'm going to put everything back at 1. We'll clear it and just you can run a test. Everything should stay the same, right at where we start. Now let's add some genetic drift. Now genetic drift is changes due to random error. And random error is most pronounced in small populations. And the reason for this is rather simple. If you have a large population, let's say you flip a coin 1,000,000 times, that's a large sample size, right? You're going to get a pretty true, a very, very close representation of what the actual system is. So if it's a perfectly balanced coin, you'll get very close to 50-50 within a small margin of error, depending on how many times you flip it. But if you flip that coin a small number of times, you have a much larger potential for sample size error. So if you flip it twice, right, there is a 25% chance that you get 2 heads. And if you use that as a measure of that coin, you say, oh, I flipped a heads the second time. Oh, this is a really biased coin. 110% of the time, I'm going to get heads. Now, hopefully you realize the flaw in that. It's that your sample size is not adequate to represent the true nature of that system that you're exploring. So the same thing. If I have 200 individuals in a population instead of 200 million or however many we had before, then there's a much wider range of stochasticity, right? This is random chances. Maybe more big A's have babies, big A's have babies than others, or maybe they mate with each other just by chance more often. And even if there's not natural selection, what we're going to have is random fluctuation. Now the point of this is it's completely random. So there's no predicting whether it will go up or down. So notice if I run this again, that one looked somewhat similar, but at the end it diverges. And if I run it a third time, I get a different outcome. And every time I do this, I get something quite different. And if we give this enough generations, let's do 1,000 generations. And at 1,000 generations, this random fluctuation is eventually going to fix one or the other alleles nearly every time. So we fixed the big A allele. But it took like 250 generations. That time we almost lost the big A allele. Then it becomes very common, goes back down again and again. It goes up, but it took almost 600 generations to fix the big A allele. And about half the time we'll randomly fix the big A allele. And about half the time we'll randomly fix the little A allele. We'll lose the big A and the little A allele will be at 100%. Now once that's done, again, that's it. There's no more random fluctuation because we don't have any more little a's in the population. Or if it's up at the top, we don't have any more big A's. Now, one last thing just to wrap this up. The direction of this fluctuation is unpredictable. So it might go down or up, right? But what is predictable, at least over the long range of this, is how much it fluctuates. So if I increase the population size by a factor of 10, 2,000 individuals instead of 200, and I run this again, we're still going to see fluctuation, but notice it's much less pronounced. We don't have as jagged a peaks and as up and down and up and down. There's still some. And so we get some. If I make it even bigger, so 10 times bigger, so now we're at 20,000, we're still going to see random fluctuations, but now notice it's much less from generation to generation. And the larger this population gets, 2 million, sorry, that's 200,000, right? We see less fluctuation. 2 million, even less. And at 2 million, we're staying pretty close, not exactly, but pretty close to that 50-50 line. And then once I get it up large enough, I'll just add lots of extra zeros. Now it's going to pretty much just always stay at 50-50 with so little fluctuation that we can't measure it even down to when we're looking at 1/1000th of a gradation there. Okay, so again, you can play around with that. Now notice we could do both in this simulator, and we'll do this in later exercises. We can have some fairly pronounced genetic drift with a small population size, and we can also have some natural selection. So let's do this. Now in this case, notice that we lose the big A allele, but not every time, right? So just by chance we had quite a number of them, but sometimes we lose the big A allele, sometimes we lose the little A allele, okay? And so that's basically, this is called underdominance. You don't need to know that now, we'll do that later. We can do basically the reverse of that, where we have, let's say, 0.8 on this side, 0.8 on this side. I've got to change one of them to 1. So we'll do the heterozygote has 1, and the homozygotes both have the same fitness level. Now, we're going to have random fluctuation, but this is going to be a force that tries to keep it in the middle. So despite that random fluctuation, whenever it gets too far, natural selection brings it right back to the middle. So in this case, we still have lots of fluctuation, but there's not the ability for it to fix one allele or the others because the natural selection is trying to keep it balanced. All right, those for the purposes of this first unit, I just want you to play around with. You can open up, click the link in that additional resources folder, play around with it a little bit. You can change natural selection, add genetic drift, do both. Just kind of get familiar with it. We'll bring this up from time to time in lectures, and you'll have some worksheets where you'll be working on this, and it can be a very valuable tool for helping you to understand the impact of the big three, which again, one more time, I know I'm saying this a lot, that means it's important. Number 1, mutation. Number 2, genetic drift. Number 2, natural selection. And number 3 is genetic drift. And all of those are the 3 big evolutionary forces that can change a population over time.